Well, hello again, everyone. For those of you just joining, I'm Mike Kruse. I am the co-founder and CTO of INZWA Technologies, and we're delighted to be presenting today's webinar. Today we have with us Dr. Rune Storesund, who's going to be presenting his presentation, Implementing Effective Risk Reduction Vibration Monitoring Programs. But before we begin, we have a couple housekeeping items that we wanted to make you aware of. The first thing is that during the presentation, we're going to be doing a little interactive component to this presentation using a tool called Menti. And as you can see there on the screen, there's a website and a code. If you'd like to participate during the presentation, please open up your browser on your phone or on your computer to menti.com and enter the code. And you'll be able to enter things there and they'll appear in the presentation as Rune asks you for those things. We are also going to be taking questions at the end of the presentation. And you'll notice at the bottom of your window, you'll see a Q&A icon. Please click that anytime you have a question and type your question there. I'll be monitoring that throughout the presentation. I'll answer questions when I can, and then we'll also present the questions at the end of Rune's talk. So without further ado, I'm going to turn it over to Rune. Rune?
All right. Well, good morning and welcome to this webinar that will provide you with an overview of monitoring elements you can implement in your construction project to more effectively reduce risk from construction-induced ground vibrations. My name is Rune Storesund. I'm based in the San Francisco Bay Area. And professionally, I wear a number of different hats. So I'm the CEO and president of Storesund Construction, as well as Storesund Consulting. And I serve as the executive director of UC-Berkeley's Center for Catastrophic Risk Management, where my research interests focus on safe and reliable socio-technical systems. The presentation today will largely be from the perspective of my forensic and litigation experiences related to construction-induced ground vibrations. Let's see if I can get my slide. There we go. So the presentation today will touch upon four primary topics. First, I'll present a very high-level overview of vibration mechanics. I'll highlight key considerations as well as best practices associated with effective construction-induced ground vibration monitoring programs. And finally, I'll present a case study and a look into the future of enhancements we can make to increase the utility and robustness of construction-induced vibration monitoring to minimize our risk exposure. So before we dive into the material, I'd be very interested in seeing what the thoughts are from the audience here on what some of the motivations might be for having a vibration monitoring program. So as Mike mentioned before, if you go to www.menti.com, punch in the code 84270333. It's also shown at the top of the slide here. We can get some feedback from the audience on what some potential motivations might be. And I suspect here that we're going to have a number of individuals that may have had some experience in the past with these construction-induced ground vibration monitoring programs. So very happy to solicit your input and thoughts and experience. Protect infrastructure. Yep, that is a good one. All right, now they're all coming in at once. Lawsuits. Yep. Nearby neighbors. Human comfort. Yes. Looks like structural damage is one that is at the forefront here, getting a lot of votes. But I think what this list illustrates is that there is a number of different motivators that go into why you would have a monitoring program in place. So thanks to everyone for participating on that particular slide. So I do want to provide a very basic background for everyone on vibration mechanics. Generally, there are three primary modes of ground vibrations that contribute to construction-induced vibrations. These are P waves or compression waves, S waves or shear waves, and R waves or surface waves. There is a fourth set of waves, love waves. They propagate in a kind of a sinuous side-to-side motion, but they're less commonly generated during your typical construction activities. The left-hand side of this plot gives you a visual depiction of the P, S, and R waves. And the right-hand side of the slide illustrates that these waves travel at different speeds through a material. Now, this is important for a couple of reasons. First, the total vibration energy is a composite of these different wave types. And second, as time elapses, because these waves travel at different speeds, they separate and the total energy is distributed. This means the further away you are from the source, the less the experienced vibration. And for most projects, the decrease in experienced vibration is going to be a non-linear one. Now, the propagation of ground vibrations is actually quite complex, and it's dependent on a number of different factors. Some of these factors include what type of construction equipment you'll be using and how that equipment will be used, the subsurface soil conditions present at your site and adjacent to your site. Do we have more uniform subsurface conditions or very heterogeneous conditions? Are there subsurface layers that might be susceptible to densification as a result of construction-induced vibrations? We can also look at what are the surface conditions. Is there a composite of materials, and how will the ground vibrations translate between one material type and another one? Say, an asphalt concrete parking lot versus a reinforced concrete parking lot. Are there other nearby sources of vibrations that could be contributing to the experienced vibrations at or near the construction site? And what's the nature of the vibration energy source? Do we have harmonic or non-harmonic waves being generated? What's the frequency and distribution of the wave energy being emitted? So, armed with this very basic background and understanding of vibration mechanics, let's examine some key considerations I'll suggest are associated with the design, implementation, and monitoring of effective risk reduction ground vibration monitoring programs. So there's an extensive list of considerations. There are unique elements associated with every project. So my advice is to approach each project with a new, fresh set of eyes and perspectives, rather than just blindly copying and pasting what was done on the last project. Things I consider when approaching a new project include distance. How large or small is the project site? And what's the proximity of the project site and proximity of the ground vibration inducing work to adjacent populated areas or structures? I'll look at population density. What's the distribution and density of people around the project site? What's the condition and anticipated foundation types of the surrounding structures? And finally, what are the specifics of the work being planned, including the proximity and the duration of the work relative to those existing structures? So here's an example of work being performed in a very dense urban environment. There's residential homes surrounding pretty much all of the work, and the access to the work areas is highly constrained. In addition, much of the residential access is going to be interrupted or totally eliminated during much of the work, which will enhance the sensitivity of adjacent residents to those construction activities. This type of work will span many months to even years, depending on the phasing. And in addition, this particular area has a number of older homes, which means it'll be susceptible to new cracking, enlargement of existing cracks, and reactivation of old or hidden cracks that may have been painted over, for example. I would be very deliberate in the development of my construction-induced ground vibration monitoring program for this type of a project setting. Now, this site is very different from the previous one we looked at. There are some residential structures off in the distance, but the project site is not situated immediately adjacent to structures. For this type of a project, we'd probably want to be sensitive to the access routes used by the construction equipment and supply trucks if those trucks and equipment access the project site through the neighborhoods. It may be that your greater risk vulnerability is going to be associated with the construction access portions of the project as opposed to the primary construction work itself. So there are many uncertainties associated with damages as a result of construction-induced ground vibrations. The occurrence of the ground vibration isn't necessarily the problem. The problem is going to be more associated with the soil structure interaction, where those ground vibrations result in some physical change in the existing structure, typically in the form of a crack, as those ground vibrations transfer from the ground into the structure through the foundation system. What was the condition of the structure before the work started? Were there any existing cracks? These existing cracks may be visible, or they may be hidden behind some wallpaper or paint. For most typical construction projects, it can be infeasible to do detailed interior and exterior surveys of every single house in the proximity of your construction project. Also, we'll need to be mindful of the fact that ground vibrations are not a direct measure of structure displacement. There are rough correlations between ground vibration velocities and the corresponding response, and unfortunately, this is not a precise science. Soil conditions can be variable beneath the construction work area. There can be zone of soil materials that may be susceptible to densification, which could, depending on its location relative to the overlying structures, result in a structural impact to those overlying structures. The variable soil conditions may also have an impact on the attenuation and propagation of the construction-induced ground vibrations. Most geotechnical subsurface exploration campaigns don't directly assess the vulnerability of subsurface soils to construction-induced ground vibrations. However, that subsurface data can be very helpful to those developing the construction-induced ground vibration monitoring program. If you have subsurface data available for your site, which hopefully is all sites, do seek out that information and review it as you configure your monitoring program. Now, I'll assume that many of the participants in the webinar today have geotechnical background or knowledge, so this should be fairly self-explanatory. But if you don't, you should empower yourself to reach out to the geotechnical engineer associated with your project and review the available subsurface conditions to make sure that there aren't any obvious zones of concern. So at the end of the day, much of the litigation associated with construction-induced ground vibrations focus on either the appearance of cracks or the enlargement and reactivation of existing cracks. Doing a crack-by-crack analysis can be very time-intensive, usually entails a high degree of uncertainty, and in my experience with the litigation world, just results in experts arguing and disagreeing with each other. There are instances where homeowners will proactively take photos of their house as construction starts. And I've seen cases where there are documented conditions with no cracks prior to the start of construction, and then documented cracks during and following completion of the construction work. And on this topic of cracking, my advice is, if you have the ability to install crack monitors on known cracks, you'll be doing yourself and your client a tremendous service, because now you have an established site-specific data point. If you can document the performance of an existing crack relative to the construction-induced ground vibrations produced at the site, you stand a much better chance of developing a vibration crack relationship for your site and suite of structures. Now, in my experience, this is rarely done, and I do appreciate that in many instances, cracks are located on private property, but you might be able to get permission from the property owner, or you may be able to locate cracks within your project area or in a public space near your project. At a minimum, I'd encourage you to make an attempt. You might just be surprised at the response. And I do also appreciate the potential vulnerability associated with these particular readings. However, if the project's been evaluated and no impacts are anticipated, these devices should confirm that hypothesis. And if you're not sure, that's likely a good prompt to pay extra close attention to the configuration of your monitoring program. So here is an example of a typical crack-by-crack analysis situation where the homeowner took photos inside their home before the construction started, and then following construction, they took another photo that showed cracking. So while there could be a number of different reasons for the appearance of the crack, it would be very difficult to definitively exclude construction-induced vibrations without a robust monitoring program in place. All right, so let's take a look at some best practices. There are a number of publications that provide guidance on the configuration of a construction-induced vibration monitoring program. They all essentially promote the same suite of actions. I don't have any one particular reference that I'd recommend, and I'm happy to address any questions at the end of the presentation when it comes to these references. And I'll also make available a link at the end of the presentation where you can download these typical references that I typically have on hand. So in my view, there are 5 primary components you'll want to be aware of when it comes to best practices associated with construction-induced ground vibrations. First, you want to do some pre-project site screening to ascertain your potential exposure to construction-induced ground vibrations. Second, depending on your exposure, are there mitigation opportunities for you to reduce or even eliminate substantial ground vibrations? Third, what sort of management actions can you implement to control vibrations during the course of your work? Fourth, what sort of representative vibration thresholds might you want to enforce on your project? And finally, what sort of monitoring equipment, data collection, and dissemination protocols are needed to help ensure your vibrations are minimized? So there are existing screening formulas you can use to evaluate the potential magnitude and spatial distribution of your ground vibrations. These formulas typically reference some sort of baseline peak particle velocity, or PPV, and that value is based on a type of equipment. And then there's a corresponding attenuation factor that scales that out over distance. And an attenuation factor is usually and generally varies from about 1 to 1.5. And the attenuation factor is based in part on the subsurface soil conditions at and near your site. Now, I note that the list of vibration source equipment and reference PPV values that are available to you through these existing documents is fairly limited. There are not established limits for every equipment type. Also, there's quite a bit of uncertainty in the attenuation factor. If you have an opportunity, you could do some initial testing at the project site with, say, a vibratory roller and an array of monitors so you can back calculate representative attenuation factors for your specific site. And one would expect that these attenuation factors would range from about 1 to 1.5. Now, there may be opportunities for the project to reduce or totally eliminate substantial ground vibrations. Installing driven pile foundations with use of pre-drilling may be a viable option depending on your subsurface conditions. Perhaps you can achieve ground improvement with jet grouting techniques instead of conventional pile driving. You might be able to use a hydraulic crusher instead of jackhammers and hoe rams. And there have even been instances where projects have relocated adjacent residents so they wouldn't be exposed to the sensations associated with the anticipated construction-induced ground vibrations. So the vibration management workflow looks something like this. We start with an inventory of the anticipated construction activities and the anticipated magnitude of vibrations that may be generated. Next, we look at the proximity of adjacent structures, which may extend for a distance of up to about 500 feet or so around the project area. Knowing the suite of potential vibration sources and proximities to adjacent structures, we can use our screening formulas to estimate the potential range of maximum PPV values and events outside of our construction limits. A pre-construction survey would be performed to document pre-existing conditions and installing crack monitors where possible. And finally, we then go ahead and deploy the vibration monitoring program. So I think folks are getting ahead of me here, but that is great. So we have another interactive poll question. So are all vibrations people feel structurally damaging vibrations? So if you log into menti.com, again, it should be the same code. I'll give this a few minutes for people to vote. And I'm going to take a slug of water. All right, we're still getting responses, and we have 23 out of 111. So a lot of you haven't voted there. I'll give you another few minutes. So are all vibrations people feel structurally damaging vibrations? So option 1 is absolutely yes. So we've got one participant that's cast a vote there. We have definitely not at 10. We have 11 at 12 now on generally no. And we have 5 with the depends on. As a geotechnical engineer, most of our answers start with, well, it depends on. So I can see that one. I'd say in almost all cases, the human perception of ground vibrations is going to be more sensitive than what's required to cause actual structural damage. So probably the generally no answer is going to be more representative. Not all vibrations that are felt by people will be structurally damaging. All right, we will continue on in our adventure here. So there are existing guidelines on generally acceptable and generally unacceptable vibration thresholds. And a couple of points to keep in mind on these thresholds. First, these are very general guidelines and don't really account for any site-specific nuance or nuances that may exist. Second, because of the ability of individuals to feel vibrations, regardless of the ability of those vibrations to cause damage, you may be faced with claims regardless of the selected threshold. That said, having a continuous record of recorded ground vibrations will enable you to assemble a more coherent and logical response to a potential claim absent this data. Note that the thresholds shown on this slide are a function of frequency. So deploying a device that not only records the peak particle velocity, but also frequency range can be very helpful. If you deploy crack monitors, you can further refine the correlation between the ground vibration and realized displacements or damage. There are a number of different types of monitoring equipment for ground vibrations and crack monitoring. Most of you are probably familiar with the conventional geophone type monitor. The far majority of these instruments are deployed in what I like to call a manual read mode. You have an individual stationed at the device to review the recordings and send out alerts if the project thresholds are exceeded. Newer technology, like the INZWA automated digital monitor, automates the recording, dissemination, and issuance of alerts. This system is basically ready to deploy out of the box, so it's a very easy setup and recording routine. It provides automated data collection, near real-time data displays and alerts, and has pre-configured web-based data screens. The system's also scalable, so you can deploy multiple sensors and view the aggregate data in your web browser. The ability to deploy a network of sensors and easily integrate that data presents substantial benefits for projects where work can occur over a very large distance, making it challenging for just one manual device to capture the full suite of vibrations that may be produced by various equipment across a very expansive project site. So here's an example of a manual read vibration device monitor setup observing construction activity. And this particular project had a specification that required the vibration monitoring to be adjacent to the closest structure. It might be debatable if the vibration technician has set up the device in what might be considered the closest structure or the location that's nearest the closest structure. But I'd say that this challenge is very common. It can be very difficult and even infeasible to be everywhere at once. Here's a typical manual vibration log one might see on a construction project. The vibration technician has set up the device at location number 1 and is recording maximum PPV values at the instrument location. The instrument location is stationary, and comments note the construction activity at various distances from the vibration monitor. The distances on this particular sheet vary between 40 feet and 100 feet. So we can see that there are 2 events that are fairly large. Event A is 0.48 inches per second, and event B is 0.54 inches per second. These are PPV values that were recorded at the device. That means that the PPV magnitude at the source was much larger, but the magnitude of this source vibration was not determined on this sheet. So if we take these readings that were recorded at the vibration monitoring location and plot them, we get something that looks like this figure on the left. The recorded values are what the instrument felt, not necessarily the adjacent structures. This approach to vibration monitoring generates a lot of uncertainty. What was the maximum PPV that the adjacent structures were exposed to? What was the propagation of the vibrations from the actual source to the adjacent structures? Was there any monitoring of cracks to correlate PPV values with crack movements? And the dissemination of the PPV values with a manual-based approach is also limited to the responsiveness and attentiveness of the individual who's overseeing the vibration monitor. So if we go back and we revisit our typical vibration monitoring situation, where the monitor is set up at a fixed location and records PPV values as the work moves up or down station from the vibration monitor, we can use our PPV formulas to back calculate what the source vibration magnitude may have been, and we can also back calculate the magnitude of the PPV value that the nearest structure may have felt. The chart on the right-hand side of the slide illustrates 4 different scenarios where I've back calculated 4 different PPV values at distances of 25 feet from the actual vibration source. I'll focus on the column where the PPV value at a distance of 25 feet was 0.5 inches per second. And let's assume for this project that the PPV threshold for sending out an alert was 0.25 inches per second. If we look at the photo and say that the distance from the construction equipment to the monitor is about 50 feet, and the distance from the nearest portion of the structure is 25 feet, we find that the vibration monitor would detect a PPV value of about 0.15 inches per second, but the structure, because it's closer, would actually see a larger PPV value closer to 0.3 inches per second, which would be above our threshold of 0.25 inches per second. The moral of this story is that it's not necessarily super helpful to know the vibrations at the monitor location. What we really want to know is what's the distribution of vibrations throughout the work area. So that brings me to our case study and illustration of the automated reporting capability we're currently collaborating on with INZWA monitors and their associated software. Now, this is an active development process for us, and we're always looking for organizations who might be interested in working with us to apply and refine our techniques. So if you out there in the audience might be interested, we'd love to hear from you, and I'll share contact information at the end of the presentation so you guys can reach out if you're interested. Now, the future vision of this construction-induced ground vibration monitoring technology is envisioned to shift from the current state of the practice, which is discrete readings at specific monitor locations where a maximum recorded PPV value is presented. Instead, our vision is to deploy a network of these sensors so we're able to back calculate the source location as well as the source magnitude of the construction vibration. From this, site-specific attenuation factors can be back calculated and a PPV distribution plot automatically generated that shows the spatial distribution of PPV magnitudes radiating out from the source location. Adding on the spatial boundary of the construction limits as a geofence, then we can use that to filter events, so only those events where the target thresholds are exceeded or are at the threshold limit are the basis for alerts being sent out. And this helps greatly minimize the amount of really irrelevant vibration alerts you might receive if you aren't tracking where those PPV values are relative to the construction work limits. So if a threshold PPV value is exceeded at or beyond the geofence, you'd get an automated alert within seconds with the date, the time, and a map showing the exceedance event. This near real-time alert can then be used to interactively manage construction operations to eliminate extended durations or multiple exceedances on your project. So I'd like to highlight the risk reduction aspects that I personally would include in our future vision of these construction-induced ground vibration monitoring programs. First, we would do our pre-work site screening and configuration analysis, as we talked about earlier in the presentation. We'd examine the anticipated construction activities and their associated equipment and potential range of PPV values. Next, we do some pre-project photo documentation around the worksite and look for opportunities to install crack monitors. As part of the site configuration, a virtual geofence would be developed that encapsulates the primary work area and establishes the spatial boundary and exceedance threshold from which automated alerts will be generated. A network of the INZWA vibration and tilt monitors would be installed across the site, initiating a full site monitoring system that provides automated data posting and alerts. And after the initial deployment of the devices, we'd take some baseline readings, which would be performed using conventional on-site construction equipment like a vibratory roller. And then the vibrations produced at these known locations and durations can be used to develop site-specific attenuation factors so we can proactively determine as well as test the functionality of all of our deployed devices. Did they record the anticipated PPV values? If not, then this gives us an opportunity to replace any faulty installations or devices prior to full-scale construction activity starting. With this system in place, we'd now be ready to receive real-time vibration monitoring notifications for instances where our threshold values were exceeded at the geofence. All right, now let's transition over to our case study, which is a bit of a hybrid case study. So the nature of the construction work and physical setting are both based on actual events, but the project data and back calculated values are going to be synthetic. Now, the actual project data has been distorted so we can help protect our case study partners. For this project, a new senior center is being constructed across several existing lots with existing structures. These structures will be demolished, the lots cleared, and foundation improvements consisting of rammed aggregate piers will be installed to limit future total and differential settlements for the structure's foundation. For this project, we deployed a network of 3 INZWA Veva III devices with cloud-based data dissemination, and the site was then used to illustrate the proposed future enhanced monitoring services. So this aerial image presents an overview of the project setting. To the north, the project is bounded by an active expressway with 3 lanes of traffic in each direction. To the south, we have an array of existing residential structures. And to the immediate east and west, the project is bordered by commercial properties. So this project consisted of the installation of rammed aggregate piers under new foundations for the structures. About 2/3 of the piers were going to be installed along the northern portion of the site, with the remaining about 1/3 of the improvements at the southern border of the site. For this project, we used the triangulation approach to deploy the vibration monitors. So we have 3 monitors in total 2 of them were placed at the southern end, closer to the residential development, and we had 1 monitor up along the expressway. And this layout then allows us for automated cross-checking of vibration data to limit false readings, alerts, and corroborate our site-specific attenuation. Next, a geofence was established around the construction perimeter for which alarms would be disseminated should the project threshold PPV values be exceeded. This part of the enhanced reporting was not functional during the actual data collection period, but we're using it for development purposes as we configure the enhanced reporting features. Now, this slide shows the equipment that was used to install the aggregate piers. A Caterpillar excavator was fitted with a vibratory drive head that was used to ram the aggregate in place. One of the installed INZWA vibration monitors is shown in the lower right-hand portion of the slide. Now, this unit was buried, and we extended the communication cable up on a survey stake so we could facilitate communication with the surrounding cell network, which was the default communication mechanism we had with the devices. This slide shows a dashboard view of the INZWA Cloud Data software page, and I've highlighted 2 events on the screen. Event A, which had a PPV value of about 2.4 inches per second on device 2, and a second event B that registered a PPV value of about 0.3 inches per second on device 1. So here's a layout of the 3 recorded PPV values recorded at the time we measured the 2.5 inches per second at location VM02 in the southeast corner of the site. For this back calculation, we'll go ahead and assume that the source was located about 25 feet away from device VM02. And we have device VM01 in the southwest corner registered a value of about 0.16 inches per second, and device VM03 along the northern portion of the site measured a value of about 0.01 inches per second, 0.007. All right, so this slide is a bit busy, but the first thing I'd like to point out is that our table in the upper right of typical vibration source amplitudes for construction equipment doesn't have an explicit entry for an aggregate rammer. And you'll likely find that the existing literature out there is short on a comprehensive catalog of all equipment and the reference PPVs. The second observation is that the value reported at VM03 at the northern portion of the site is probably an erroneous number. VM03 is closer to the vibration source and would likely have a greater value than the reported value at VM01 in the southwest corner of the site. We can do a sanity check on both of these using our PPV equations. We can also do some checking on site attenuation by varying the site attenuation factor. In this example, I've used an attenuation factor of 1.1 and 1.4. And what we find is that the site attenuation factor of 1.1 and a vibration PPV of 2.5 at a distance of 25 feet yields an anticipated PPV value of about 0.15 at a distance of 320 feet, which matches the value that we have at VM01 pretty nicely. So the calculated value of 0.3 inches per second at the location of VM03, I think makes sense, since this location is closer to the source than VM01. This tells me that we may have a problem with sensor VM03, or there could be some unique site condition, but my money would be on the problematic sensor. So this is what the radiated vibration propagation would look like emanating from our event A source. So here's that same vibration propagation, but with our foundation layout and geofence added in. As you can see, the propagation of the construction-induced vibrations for this hypothetical example radiates out into the residential neighborhood, which is something we would not likely want. We want to limit this. So the nice thing about these automated alerts with these attenuation maps is you quickly understand the event and its implications. So here's another example. Now we're looking at event B. But for this example, we're going to back calculate the location and the magnitude of the event B source. We recorded a PPV of about 0.3 at VMO1, a PPV of about 0.2 at VMO2, and a PPV of about 0.01 at VMO3. And as we talked about on the previous slide, I'm going to interpret VMO3 as a defective monitor. This is one of the nice features of having multiple devices on a site. If there's some sort of problem with one of the devices, you still have 2 remaining devices you can use on for your evaluation. So I can generate several equations and constrain the answer so it falls within the established geofence. I'm not at liberty to discuss all the algorithms at work here. That part's a bit proprietary. But what I can say is that we essentially have 2 equations, 2 unknowns, so we should be able to back calculate a rational solution. So here's a plot showing the back calculated origin of the vibration source using the recorded values from VMO1 in the southwest corner of the construction area and VMO2 in the southeast corner. This slide shows the vibration attenuation from event B now radiating out from the back calculated source location. As you can see, this hypothetical event also has more impact in the residential area than desired. So receiving this sort of automated alert is much more meaningful and helpful for interactive risk reduction than an arbitrary PPV reading at some monitor location. What we really care about is the PPV propagating from the source, not an isolated PPV reading at an instrument location. So this slide just recaps the construction-induced ground vibration risk reduction elements. I think the INZWA system is really helpful here because it's pre-configured, easily set up, rapidly deployed, and has the pre-established web-based reporting and alerting system. And as I mentioned at the beginning of our case study, the enhanced reporting feature is still in development. But if you're interested, we'd love to hear from you and work with you as we build out this capability. And to close, I just wanted to quickly recap on what we talked about. We started off with a very high-level overview of vibration mechanics. Next, we talked about some key considerations in developing and deploying your construction-induced vibration monitoring program, along with some best practices. And finally, we ended with a case study and a look into the future of construction ground-induced vibration monitoring and enhanced reporting capabilities of the future. So with that, we can move to questions if there are any. And Mike is our overseer of questions.
Thanks, Rune. Yep, we have 6 questions so far. The first, how do we identify whether the cracks are developed from settlement, such as compaction, or construction vibration?
So it depends, right? If this is a crack that you're monitoring in advance, and you have a crack monitor on it, then you will be able to correlate that with the location where the compaction was taking place. Typically, compaction is a directed construction activity on the site. So you're backfilling a trench or doing some sort of fill placement. The settlement that happens at that location would be directly related to the compactive efforts, but all compaction energy generates vibrations, and so they will radiate out from where that work is happening. So if you have cracks appearing at locations where you didn't directly do the compaction work, that's likely a vibration-induced occurrence.
Thank you. Number 2, what levels of vibrations are considered high before considering a vibration monitoring program?
That one really depends. It depends on the situation that you're located in. I did include and I have links here to some of these references. You can look at those. They've got some guidance relative to what type of potential damage may occur based on soil conditions at the site. You've got values that range anywhere from like a 0.1 inch per second for sensitive structures to as high as 1 or 2 inches per second for other structures that are far more robust and capable of taking damage. So it really depends on the structure that you have, its susceptibility to movements, and the ability for the site to propagate your vibrations.
Question 3, can a generally recognized non-damaging vibration level rise to the level of damage based on the duration of the events? As you initially described, house is located next to a long-term haul road.
Let's see. Can you repeat the first part of that question? It was, is this a small vibration that's happening over a long period of time? Is that?
Yeah, I think that's fundamentally what the question is about. Is can non-damaging vibration, or the vibrations that are generally recognized as non-damaging, rise to the level of damage based on the duration of the event?
So I'm not sure that the research literature out there has a strong correlation between duration and magnitude of event. It would definitely be something that I would be concerned about. But I'm not sure that there's anything that's specifically established in terms of duration and impacts on damage. Again, my suspicion would be it would be something I would be concerned about and would want to track and monitor for sure.
All right, the next question. How can the response time of geophones be associated with piezometer readings, for pore pressure buildup?
Well, most of the data or the field data collection is going to be a time series. So there's going to be a date and a time. If you've got coordination between the date and the time of your ground vibrations and the date and the time in your piezometers, you can reactively go back and make correlations between the ground vibrations and what you were seeing in the piezometer. If you have your piezometer array also connected to the web, you can make that more near real time as well. But I would suspect the way you would link those is through the date and the time.
Okay. How many measuring devices would be needed for a site, say a 200-foot by 200-foot site, would be required to realistically obtain a plot of the PPV distribution of the site?
So my default answer is going to be I like starting off with 3. Probably the bare minimum you would want to do is 2. It's hard to do much triangulation with just 1 sensor out there. But if you have at least 3 sensors, even though it's a small site, you've got that backup, that redundancy, that extra check. So if something does go awry, you still have 2 functional devices. So I would say I would recommend 3, but you could potentially get away with as little as 2. I think 1 would be too few.
Do you ever consider VDB values when determining human annoyance to vibration as opposed to cosmetic or structural building damage?
Do I consider PPV values?
No, vibration measured in decibels, so VDB.
Each site is somewhat unique and different, so there's a number of different factors you can look at. I mean, the reality is people are going to feel the ground vibrations much sooner before they become damaging, either in terms of cosmetic or fully structural. So I think having a communication program associated with the construction work in advance so you can manage those expectations is probably the best investment you can do on your risk management from the perception of whatever the characterization of the vibration is going to be.
Okay. How do we consider the effect of peak particle velocities on a structure if we don't measure vibrations directly on them?
Yeah, so I think measuring vibrations on the structure is a great, wonderful idea. Again, you're going to have different soil conditions. You're going to have different foundation types. There are some correlations out there But if you're able to instrument not just the ground, but the structure itself, now you're going to have very actionable site-specific data that is going to be very useful in establishing kind of what that soil structure interaction is going to be. So absolutely, if you have the ability to attach instruments onto structures as well, I would absolutely fold that into my monitoring program.
All right. All right. So this comment, there's a visible comment and question. Thanks, Rune, for the presentation. It was interesting. Have you looked at historically available INSAR and LiDAR data to fine-tune location plans? Thinking it might help to position monitors so as to have more redundancies in areas more at risk.
Yeah, so what I would say is part of the pre-project kind of planning assessment, you'll want to use kind of all available information that you have. INSAR and LiDAR are going to provide some elevational type information that you may not get from an aerial photo. But I would start with what's the nature of the work. So start with the project plans, the project limits, looking at the access. It's fairly easy to overlay that with aerial imagery. And then if you can drape on top of that aerial LiDAR or INSAR, that can also be helpful. But you definitely want to start with having a strong, solid understanding of what the nature of the work is going to be, the phasing of that work, and what type of equipment you expect to be out on site.
Okay. You said all compactive efforts create vibrations. How does a non-vibratory backhoe sheep's foot roller affect nearby structures? And this cause close-in displacements?
So the sheep's foot compactor roller actually does generate some vibrations as it rolls on top of the soils. The magnitude of that is going to be less. So I think that would be a wonderful illustration of managing the construction equipment and the method so that you're using approaches that have lower magnitude vibrations.
Okay. You recommend in one of your slides to install analog crack monitoring instruments in structure, but where should we install it? How do we recognize a potential crack in the structure, any specific area?
So typically, as part of a pre-site assessment, folks will walk around and cracks will be fairly evident. These might be cracks on backsides of buildings. If we go back to our little project site here, we have our project site abuts. Can you see my cursor? Mike, is my cursor? Do you see my cursor?
Yes, I do see your cursor. Sorry.
So here our project site abuts these existing commercial structures. If there are cracks in the walls, those are going to be pretty obvious, and those would be things that would be fairly straightforward for you to put some crack monitors on to see if things are shifting and moving. The residential structures, they might be a little more difficult because there's an alleyway, and these structures are not directly abutting our project site over here. So it depends on kind of the layout, the configuration of your particular site, what the opportunities are. There may be cracks on sidewalks or things out here. It's just a function of the opportunities you see when you do kind of an initial site assessment of the site, looking to see if there's any obvious cracking that's visible as part of your assessment.
What is your recommended vibration isolation trench depth, if it was possible to construct one?
Yeah, so there's been some research on putting in isolation trenches. Again, it's going to vary on the site, and it varies on the type of construction that you're doing. So I'm not sure that I have a general answer. It would just depend on site by site. Typically, I haven't seen a lot of isolation trenches used for that purpose. A lot of times there just isn't the space available on the site to implement that sort of a technique.
Do you take into consideration vibration frequency and potential for resonance when completing a vibration monitoring plan, i.e., if rock chipping occurs at 100 hertz vibration resonance, is less likely in a residential structure versus 15 hertz from hammer pile driving?
Yes. So looking at the construction equipment and the types of vibrations that they produce is part of the assessment that you should be doing. And I did mention on the threshold slides that are out there, let me pull that one up, that they're a function of frequency. So you'll want to take a look at the frequency of the construction equipment that you'll be working with, the durations, and then as best you can, the potential response from surrounding structures.
Are there opportunities / scenarios to start vibration monitoring design by collecting related soil vibration / attenuation data during a site investigation program, i.e. vibration monitoring of SPT hammer testing and correlated to future construction pile driving?
I think that's a wonderful suggestion. And yeah, if you have the opportunity to do that, I think that would be a wonderful element to fold into the project configuration and design. And this is something that the geotechs can suggest to their clients as part of the initial geotechnical characterization of the site. And I think it would provide very helpful, useful information down the stage when you start actually putting together the construction vibration monitoring plan.
All right. Could vibration monitors mounted directly on neighboring structures be used to triangulate source location the same way you've used the ground-mounted devices? Or does the soil structure interaction make the calculation unreliable?
Well, for all of these calculations, I'm going to encourage that you do some site-specific kind of sanity checking and cross-checking. So I would suspect that there is going to be a relationship between the vibrations and whether the device is installed in the ground or on the structure. You just need to establish what that kind of soil structure interaction looks like and what effect it has on the propagation of the vibration. So you'd want to do some site-specific checking, but you could absolutely have devices on structures in the ground. I'd probably recommend both in the ground and on the structure as opposed to just on the structures, because now you're not able to take advantage of kind of the established relationships for in the ground monitoring, right? You're going into kind of a new condition that has a whole set of additional uncertainties built into it as well.
Okay, and our last question. If requested by the owner of a neighboring multi-story building to place seismographs inside the building, would you place them on the top level of a multi-level building or at the ground level?
I'm kind of a data collection person, so I would install them at both locations, the ground and the top. That structure is probably going to behave differently depending on where you are, the frequency of the vibrations, the durations, and if you can monitor the lower and the upper level, right? And if our pre-screening tells us that we shouldn't have a problem, I now have 2 data points that show I don't have a problem as opposed to just one. So I would go for the monitoring both the upper and the lower.
All right. And we actually have one more question sneak in right here at the end. So this question is, in general, is the higher the frequency recorded from the equipment at the structure better?
So I'm going to interpret that question like, do I take a sample every second as opposed to every 5 minutes? Is that, Mike, you think a correct interpretation?
That's what I think of the way I would interpret it too.
Yeah. Yeah. So it probably is not going to be helpful for you to just take a snapshot recording every hour or 10 minutes. You want to, and Mike, you can probably speak to the sampling rates that you guys have built into your devices, but really what you care about are these exceedance events. And you want your sampling rate high enough so that you can make sure that you capture an exceedance event or a high event or low events, right? So you can say, hey, there is no problem out here because all of our vibrations have been less than whatever your threshold number is. I would suspect it would be a sampling rate on some less than a second. What's your typical sampling rate, Mike?
Well, the typical sampling rates are 1,000 samples per second or greater, kind of depending on the maximum frequency that you anticipate. And we generally recommend a sampling rate of 10 times the anticipated high frequency. So as an example, if you expect 200 hertz as a high frequency, then sample rate should be 2,000 or higher.
Perfect.
Okay. All right. I think that's all the questions for now.
Great. Well, thanks everybody. And you know, like we mentioned, if you're interested in some of these kind of advanced reporting features, don't hesitate, reach out. We'd love to work with you and apply this as many different contexts and situations as possible. So
yep.
Look forward to hearing from you.
And one other quick note before everyone leaves, we will be distributing the recording of this presentation in the next couple of days, so you'll be able to review. And you're always welcome to reach out with questions. So thanks everybody for attending, and hope you have a great rest of your day.
Thank you.
Thank you.